There we go. Thanks, Harrison.
It's still green.
Almost screwed everything up.
It's still green.
It's green.
Sorry. Bad definition. Doesn't say red REC, I should have said. Thank you. Good man, good man. Now, here's the deal. I'm going to give you a series of experiments, some of which are a little more convoluted than others. And you're going to tell me whether or not it's binomial based on the conditions of what we'd seen with the chickens and so forth. So here's what we've done before. You roll a single die and count how many pips you get. Is that binomial?
No.
I'm hearing votes for no. Okay. Tell me why. Hattie, tell me why it's not.
Because you could roll a 1, a 3, a 6, 4, 5, and a 2.
Well, there you go. That's not binomial, that's hexanomial, right? That's not 2, that's 6. So it's not a binomial, therefore you couldn't use the binomial section of that program to actually simulate this distribution. You could do the one called the uniform distribution. There's a uniform option in there. If you're interested, you can mess around with that. But that right there is not binomial because you've got too many outcomes. You're keeping track of pips, not the presence or absence of a pip. Fair, is that fair enough? Not binomial, therefore doesn't govern what we're talking about right now. All right, how about this? I changed it a little bit. You're still rolling a die, but now you're going to bet on 3. Is that binomial? Jenny says yes. We in agreement? Why is this binomial?
So you can either get 3 or not.
That's the difference. We took all 6 of those outcomes and broke them into 2. Getting a 3 or not getting a 3. Perfect. That can be binomial. How would you enter that distribution into your TIs? How would you enter that distribution into your TIs? Let's practice that too. For everything that's binomial, let's get it into our TIs and make sure we know how to enter it, yes? Make sure we can see this as well. Let's pull it back a smidge. There we go. Hold that thought. Hold that thought, Harrison. That was beautiful. So let's fire it up. Program distfill. Okay, so remember what we're doing. We're betting on 3. We're rolling a die and betting on 3. What variable are we measuring?
The pit one. Is it 3 or what?
Be more specific.
What number you're rolling?
Well, correct. So if we're betting on 3, what do we care about?
If
If it's a 3 or not. So what's the least number of 3s we could get? We might not get any, or we might get 1. It's a pretty simple distribution. You're either going to get no pips, or no 3s, excuse me, or you're going to get 1 3. It's a very boring distribution. It's like buying 1 chicken and rolling a die and seeing what you get. And it's binomial. Yes, it's binomial. With a probability of 1/6, because that's the chance of getting a 3. 1 in 6. And then it says done, and you're going to look at it, and hopefully that looks exactly as you would expect it to look. There's a 5/6 or 83% chance of not getting any 3s. There's a 1/6 chance of getting 1 3. Very simple distribution, very small, like buying 1 chick, either getting a rooster or getting a chicken. Is that cool? So there you go. You have to keep track, and always ask yourself, what variable am I interested in measuring? What am I measuring? It's not. It's correct to say you're interested in the number of pips that you get, but only because you bet on 3. So you're more interested in whether you got a 3 or not. Does that make sense? Now you have to count the pips for that, obviously. You have to count the pips for that, obviously, but you're more interested in the number of 3s that you get. Cool so far? Okay, here we go. Oh, there we go. We've done this one in class as well. Rolling 2 dice, and counting the pips that you get by adding the dice together. Binomial. I hate that. No. No! That is nice. No! Why is it not?
It's not binomial.
Heather, help me.
It's not really like probability of rolling.
Well, I could say the probability of getting like a 6. If I get 3 and 3 or 4 and 2.
It's not one or the other. There's multiple.
That's the problem, right? The problem is you can get snake eyes, you can get boxcars, you can get 7, you can get 8, you can get. There's always ways you can roll 2 dice to get all these outcomes. I think there's 11 different sums you can get, right? That's a challenge. So it's 11 nomial, not binomial. That's a problem. So that's not binomial. Okay. How about this one? So this is kind of like craps diluted down a little bit. So here's a pair of dice. What do you think?
Are you saying you're either going to get 7 or 11, or are you saying you're betting on 7 and 11?
I'm letting you decide. Can you make this? Let me ask you about it. Can you make this binomial? What are you interested in when you gamble? When you gamble, what are you interested in doing? You either win or you don't. Can we put this in the? Can we couch this in the context of winning or not winning? I think we can. I think we can make this winning or not winning. So we're gonna roll our dice, and let's let X, hang on a second now, let me raise the screen for a sec, to get some board. I'm not saying that you can treat this not as a binomial, because I think you can treat it not as a binomial, yes. But if you say X equals the number of times that you win, which would kind of equate to the number of times you rolled a 3 before in the previous example. If you're only throwing the dice one time, how many times could you win? Well, you might not, or you might. So this is kind of like rolling the 3 and betting on the 3. You're either going to roll the 3 first, or you're not going to roll the 3 first. Is that fair?
Yeah.
And then we can fill this column in. Well, actually, we'll come back to that. We'll do that in the TI. But I think we can make this binomial. Those of you that are saying it's not, I can agree with that as well. You would just define your random variable differently. You would say X equals the pip sum that you got. So you might put 7, and then 11, and then everything else, I guess. Yeah. But you can make this binomial, yes? You either win or you lose, based on the results. Is that fair? Okay, good. So let's scroll this down. And then get back over, because I have one more, I think, slide in there. Let's go back to our program, yes? So program, binomial. Oops, wrong program. That's the old version. Doesn't work. Oh, speaking of which, I'm glad I did that actually. If at any time when you guys are running your programs and you inadvertently press a button that comes up with a break, this will happen occasionally. You can press either button. It's probably safest to go to quit instead of go to. A lot of students go to go to, and what it does is it takes you into the program, which is fine. But the problem is, then they start panicking and they start pressing buttons to get out, and you end up either deleting lines or adding lines, and then the program doesn't work. So what you might want to do, if you ever get that error, just quit. Just quit. Don't go to. Just quit and then start again. Does that make sense? If anything happens, it's not that big a deal. I just need the program again and overwrite it and fix it. But if you're at home doing homework and you're getting wrong answers, that could be one of the reasons. Okay, anyway, back to dist fill. Here we go. Smallest X. I'm going to go with 0, largest X. We're only betting one time so far. We're throwing the dice one time. We'll see what happens. We are going to win binomially if we roll a 7 or 11. What is the chance of winning? 2 and 36 is the number of ways to get 11s. How many ways can you get 7? You remember this? I think I was ever saying that. Count them, right? We know it's out of 36, yes? How many ways can you get a 7? Go. 4 and 3. 3 and 4. 5 and 2. There we go. 2 and 5. 6 and 1. 1 and 6. There's 6 ways to get a 7. 2 additional ways to get 11. 8 and 36 altogether. 8 and 36 is the chance of winning this bet. That's your chance of winning. 8 and 36, yes? Just under 25%. Done! Go look at it. There you go. There's the chance you win. There's the chance you don't. 22% to 78%. There's your chances. How's that? Does that make sense? Everybody, did the 8 thing just freak you out? Class got really quiet all of a sudden. The 8 thing was okay. It's just, I'm calling it back from a couple days ago. I had you guys actually turning the dice in your hands a couple days ago. Now this is if you play the game one time. This is just playing the game one time. But you often don't. You often play the game multiple times. So I'm going to do one more, then we'll take our 5. What if you do that same game 5 times? How would that change the distribution now? Each time betting on 7 or 11.
Would your L1 column just go from 0 to 5?
Boom! Everybody hear that? Jenny, say it nice and loud.
The L1 column would just go from 0 to 5?
Where the L1 column used to be 0, 1, this limits it to winning either not at all or winning 1 time. But you're playing 5 times now. You could still lose all 5 times. You could. You could still win 1 time, which meant you lost 4 times. But you could also win twice and lose 3 times. You could also win 3 times and lose twice. You could see, this gets hard to keep track of though, which is why I gave you the gift of technology. And then you can calculate on average how many times you're going to win. So let's figure it out. Let's figure it out. Run the program again.
My bet is you should only play it once.
Hold that thought. We'll come back to it.
Yeah.
Always
It's hard for me to coach you on that. Because gambling should be fun. It should be enjoyable. It should be like going to the movies or anything else. But people lose track of that sometimes. Since money is involved, changing hands. So let's go 0 to 5, yes? Is everybody following the logic of 0 to 5 on this one? It's like sending Max into the bin and getting 5 birds. You're either going to win or lose, chicken or rooster each time. All you got to do is view it as buying chickens. It's binomial. And you're still going to win with 836 probability, aren't you? It's still 836 because each time you play, there's an 8 in 36 chance of you winning. Yes. 8/36. It's done. Go look. There you go. Do you remember what Kate said? Do you remember what Kate said? She said play once. Now this is a little bit tricky. The most likely outcome, 40% of the time, you're going to win once, but you're going to lose 4 times. That's what that indicates. Remember, this random variable, x here, is number of times you win out of 5. So the most frequent outcome is you're going to win once out of the 4. But that should make sense. The chance of winning is roughly 25%. I'm going to make it 25% just to make the math easier for us. 0.22, it's about 0.25. Times 5 trials. 5 times 0.25 is 1.25. That's about 1. That's the average number of times you should win out of 5. The rate of success applied across the trials, it's about 1. But look, these aren't that unlikely either, are they?
It's been really good.
Now think about this. There's a 23% chance you're going to win twice and lose 3 times. There's a 40% chance you're going to win once and lose 4 times. There's a 28% chance you're not going to win at all. 28% FYI, we could have gotten that very easily by doing, what was it, 8/36 chance of winning. So that means there's whatever's left. This is my head. 18? No, 28. 28 out of 36% chance of losing. 28 out of 36 to the 5th power is that number. So if you add these 3 up, what do you get? I get 91, I think, 91%. There's a 91% chance you're going to win no more than 2 times. This is a fantastic game for a casino. Because they charge you money to play it, yes? But look how rare these are getting down here. About a 7% chance of winning 3 times and losing twice. So as soon as your wins switch over to you're winning more than you're losing, the probabilities drop off. Brilliant. Absolutely brilliant from a casino point of view, yes?
Yeah.
There you go. If you're interested, and we'll take a break after this, I gave you a second program called Dist Draw. If you look at that one, once you've run Dist Fill, you can run Dist Draw, and all that does is it gives you a graph of the distribution. And it's a pretty low-res graph. It's not like Excel. Excel's a much better graph. But you can trace this now as well. So you can hit the trace button, and then you'll recognize these from the chart, L1 and L2. So the x, the random variable x with its probability, there's your 1, 41%, and so forth and so on. And for those of you that want that second dimension, instead of just having it in a t-table, you've got a graphic this way too. Most students never use it, but I figured I'd have it just in case you wanted a 2D look at it. Cool? Awesome. Let's take 5. You got that glazed look. Let's take 5. We'll come back and we'll do some more. Is it binomial? Is it not? And then we'll see where to go from there. Oh, great. If you want to go through that folder, you're